introduce Eulalia Nualart, who I'm always hating that. Whose title, I'm afraid I don't know.
Well, it's a strict positivity for the density of I don't remember which title I got. No, it's the title of my paper. The strict positivity density for nonlinear spatially homogeneous SPDEs. Okay, thank you for the invitation. Okay, so I'm interested in the following class of SPDEs: LUTX equals sigma UTX W dot TX UTX UTX. Right, so T is time, and X is in RD with D bigger than 1. So spatial dimension bigger than 1. And the noise is a family of 0 mean random Gaussian random variables indexed by functions in symphony with compact support in 0t times RD. And the covariance of the noise, it's going to be white in time and some spatial covariance in space. So psi. So it's going to be phi tx. So f will be the covariance in space, which is assumed to depend on t minus x and y minus x. And okay, so this means that this is white in time, and f is the spatial covariance. Okay, right. So in order to this to be positive definite, one necessary and sufficient condition is f to be symmetric. So this is equivalent. So f symmetric. So this is equivalent to say that f is the Fourier transform of a tempered measure, right? Which means that there exists some integer such that integral in RD mu c is fine. Okay, and sigma and b are globally Lipschitz functions. Okay, right. So for the examples I'm interested in. So L here represents a second order differential operator, and the examples I will be interested in are wave equation and heat equation, right? So for example, L being the heat operator, or L being wave operator, right? And also examples of F will be, for example, the Rich kernel, one. Okay, and in this case, the tempered measure is just, it's absolutely continuous with respect to the back measure, of course, and it's C beta minus D xi. Okay, right. So in order to make sense of these nonlinear SPDEs, one defines the mild formulation to be, so one defines a solution of this equation to be UTX, so the adapted process in tree satisfying the following integral equation: UTX integral between 0 and t of gamma t minus s x minus y sigma usy w ds dy plus integral between 0 and t and x minus y gamma s dy yes. Where gamma is the fundamental solution of the deterministic equation LU equals 0. Okay? Right, so one needs to make, in order to prove existence and uniqueness, first one needs to make sense to the stochastic interval. Okay? So in the case where the solution of the deterministic equation is a function, Okay, this is Walsh stochastic integral. Okay, but in the case where gamma is a measure, one needs to define what does it mean, what this integral means. Okay, so for example, in the wave equation in dimension 3, the solution is the measure gamma is the surface measure on the sphere of radius t in R3 divided by 4pt. Right. So for example, in this case, so for a heat equation, it's the green function, the usual green function. But for the wave equation dimension 3, gamma is a measure. Okay. And then, well, so this has been defined in the literature. There's the pioneer work or the work by Dalan and Frangos. Right? So they extended Walsh stochastic integral to make sense of this type of integrals using techniques of Fourier analysis. Okay? And then there is a more recent paper by Eulalia Nualart and Louis Kerr, where they use the theory by stochastic integral with respect to cylindrical binary process by the Praton's object to make a sense of this integral. Okay, and essentially what they do is that so they define H to be the completion of the rapidly decreasing functions which are C infinite with respect to the scalar product integral RD. So let's say scalar product S. C1. Okay, so they start defining H to be the completion of the rapidly C infinite decreasing function with respect to the scalar product in terms of the covariance function, and then they define HT to be L2 functions taking values in H. Okay, so this space this might contain distributions, and so one can extend this family of Gaussian randoms in the usual way to a family of Gaussian random variables indexed by this space HT, right? Then in particular, one can do Malevin calculus in this Gaussian isonormal space, okay, in the usual way. And so the assumptions then that they have, so that what one needs to prove is that gamma is in HT, right? In order to define this as an integral with respect to a cylindrical binary process, right? And the conditions for gamma to be in HT, so the hypothesis that they have is that gamma is a non-decreasing distribution with rapid decrease, such that we'll call this quantity GT, the integral between G and T, integral of D, the Fourier transform of gamma of C squared with C dt is fine. Right? So under these conditions, then they prove that gamma is in HT. And this is exactly the norm of gamma squared in HT. Okay? That's what they prove. And then, well, in order to this be well defined, they also need the hypothesis that gamma is a non-negative measure. Gamma is a non-negative of the form gamma T dx dt, such that the supremum of T is 0T, the integral now D of gamma T dx is less than some constant. Okay? Right, so for example, in these examples here, so for the heat equation, the solution is the Gaussian density. But for the wave equation, the only case where we have a non-negative measure is for d equal 3, or 1 and 2 is a function. Okay, so for d bigger than 4, this theory doesn't apply. Right? So the only case where this defines a non-negative measure is d equal 1 to 3, and here d is equal and equal to 1. Okay, and this condition here, in order to have a solution of this, is that even only if the integral in RD of mu dxc divided by 1 plus c squared is fine. Okay. So in particular for this is, so we need the condition better to be less than d in order to have this condition to be fulfilled. Okay. Okay, so under these assumptions and sigma b globally Lipschitz, they prove using the method, the well-known method by Dalang, that there is a unique adapted process and continuous in L2 that satisfies this equation. Okay?
What did you say about sigma? Sorry.
Lipschitz, globally Lipschitz for existence. And okay, so we have the existence of a unique adapted process, continuous in L2 and adapted, such that with final moments. Right? Well, I forgot to say that, of course, okay, so they prove gamma is NHT, but they also need to prove that gamma times sigma u is predictable, okay, of course. And they prove that this is predictable if sigma u is predictable, is a predictable process. Okay. Okay. So the second thing that they are interested is the existence of the density of UTX for TX fixed, right? So what they prove is that the sigma and b are say infinite with bounded derivatives. Then, and that sigma is non-degenerate. Then, and they also need another condition on these objects. So they need that for all, so in G01, G of O to be lower bounded by some constant, so gamma 1. So there exists a gamma 1 such that for any tau this is lower bounded. Okay? So under this condition they prove that there exists a same infinite density, let's call it PTX. Okay, using the usual methods of Mariam and Kakula. So for example, in the case of heat and wave equation, so for a wave equation, this is satisfied for all gamma 1 bigger than or equal to 0. And for wave equation dimension 1 to 3, so this is for heat. And for wave equation, this is satisfied for gamma 1 equal to 3. Heat, wave. In any dimension 1, 2, and 3. Okay? Right. So, so I am first interested, so the first problem I look at that is this density positive, strictly positive, okay? So, is PTX strictly positive? Okay, so this is the first problem I look at, and the theorem I have is the following theorem. So first of all, I wanted to prove a more general result. So first of all, I proved that the sigma and b are, say, infinite with bounded derivatives and bounded derivatives, and this constitution and for all so G1 G of lower bound C tau gamma 1, then UTX has the same infinite density of the open subset of our let's say sigma sigma y equal to 0. Okay, so this is just a slightly modification of their theorem, just considering the Malevin matrix, so proving that the Malevin matrix has all moments in this set. Okay, so this is just a slightly modification of it. And then secondly, I prove that, so for the strict positivity, so I was able to prove strict positivity under the conditions of if PTX is continuous, and sigma is bounded, then PTX is strictly positive on the connected component of sigma that contains 0. Okay, so I prove the strict positivity assuming that there exists a continuous density. Okay, and I need the additional assumption sigma to be bounded, which is not used for the first one. And then I prove that the density is strictly positive on the connected component of sigma that contains 0, which means, for example, that for example, imagine that sigma is minus 1, 1 complementary. Okay, which means that sigma doesn't vanish, but vanish only minus 1 and 1. And imagine that the support is minus 1 and 1. Right, so what we have is that the density is strictly positive on the interval minus 1 and 1. Okay, but of course not necessarily on the other connecting component. I'm assuming initial 0 conditions. That was your question?
Well, it's one of my 2 questions.
Yeah. That I'm assuming that 0 is in the support, so I'm assuming that.
Right. So G is just this.
G is this, yeah. Which in the wave and heat equation is just this.
That means somehow that the total energy of the.
Oh, you want to see this in terms of energy?
I want to understand what that is.
Well, this is the HT norm of gamma. Okay. Right. So. Right, so how do one prove these results? So the continuity. So this result is proved in the usual way, and to prove these results, so proof of the strict positivity. So it suffices to prove that for all y in the support of the solution of the law intersection sigma, and for all f continuous bounded positive function with support contained in sigma, we can write the expectation of f utx, which is the integral of r fz ptxz. If I prove that this can be lower bounded by the integral in r of fz by some function theta of y z df, where this function is continuous positive and theta y of y is strictly positive. If I prove this, then I get that the density is strictly positive for all y in the support intersection sigma. But this also proves that the connected, this implies this, and this also shows that the connected component of sigma that contains 0 is included in the support. Of sigma that contains 0 in the support, so that the density is strictly positive in all point of this connected component. If this is not true, just take a point on the boundary end of the support, for example here, as the example. Okay, then and then use the fact that the density is continuous. So a point on the boundary of the support where sigma doesn't vanish, then the density needs to be strictly positive, but this is a contradiction with the fact that the density is 0, right? Yes?
So you're not using anything about the Malevin matrix to get the positivity, you're just using that to get the existence of the PT, right?
Right, for the existence of the PT, you already have
but then
proof moments, and then for the proof of this, I will use the non-degeneracy of sigma, but nothing on the Malevin derivative.
And that's
nothing on the Malevin matrix.
Right, that was my question.
No.
And the function theta, can I think of that as somehow being associated to the free field?
What is the free field?
The field without the B or without the.
Not exactly.
I mean without the with sigma times its lower bound. I mean W dot times sigma lower bound. I mean sigma has a lower bound, right? Locally.
Right.
So I can just.
What I'm doing is I'm doing a shift of the noise. I'm going to explain this.
Okay.
Yeah, we show.
I thought you were
So
stopping
no.
Okay.
No. Now I will show the idea of this.
All right.
No. Just to say that. So this is just to say that it suffices to prove it for y in the support intersection sigma, because then I get that. And now let's talk about how do we get that. So maybe I can continue here. So in order to prove that, I use a real variable lemma that says, so there's a real variable lemma that says that for all beta and data fixed, there exists an R in 0, 1 and alpha bigger than 0, that for all G from R to R C2, such that. So let me write it as, so here G has just one dimension, but in the second part of the talk I will talk a little bit about one dimension things. So the support of X okay, so I have, if a function satisfies these two conditions, then is a diffeomorphism from a neighborhood of 0 contained in the ball of 0R to the ball of G0 alpha. Yeah, okay. So under these two conditions, I can construct a diffeomorphism. Okay, so I'm going to use this real variable lemma. Let's see how. So, so what I do is a transformation of the noise, so a shift of the noise. So I fix, so for H fixed and Gn a sequence of predictable process in HT, and Z fixed. So fix all these quantities and define the following cylindrical Wiener process, 0T and H. So it's my Wiener process plus the shift Z integral between 0 and T H GNS of H ds, sorry. Okay, so this is the shift process on the direction Z times G and S, right? So by the Girsanov theorem, for example, from the book of by the pattern subject, this is also, there is a probability measure where this is a cylindrical linear process. Okay? Right, so the idea is to apply this Girsanov theorem to my expectation of f utx. So using Girsanov theorem, I can write this as, so G, well maybe G is not a good idea. I don't know, f. So f of z is any strictly positive. For example, take the Gaussian density on any strictly positive continuous function, such as integral of f is 1. Then one can write using this Girsanov transformation expectation as f, and u hat is now the solution of our SPDE under this shift noise. Okay. So u hat and gx, and gzn is the random variable, which is the exponential. Z is the random variable from the Girsanov theorem minus z. E to the power g, e to the power g, g and w minus 1/2 z squared. Gn square h. Okay. Okay, so using Girsanov, one can prove that. And then the idea is to use the lemma and to use the change of variables theorem, the usual change of variables theorem, and apply this lemma to the diffeomorphism z that goes to u, and so there's some z going on. Right? So the idea is to localize this under a set where these conditions hold, so that this defines a diffeomorphism. Okay? And then use the change of variables theorem to prove the existence of this function theta y of z. Right? So in particular, the Jacobian of this transformation will be the derivative with respect to z of u hat z that can be viewed as a directional derivative, so it's a Malevin derivative. Okay. So I don't want to write all the details, but the idea is this. Right? Here I have my fz, u hat, and ztx, gzn, right? So I choose in a good way my theta n, such that this process u satisfies this in probability when n is sufficiently big, right? And this is going to be proved. So here it's where I'm going to use the fact that sigma is non-degenerate, and these are bounds for Malevin derivatives that can be bounded above. Okay, so everything is so the hypothesis of the lemma are proved using the fact that when you differentiate z of u hat and zt of x, this can be viewed as the Malevin derivative of u hat and ztx in the direction of g on ergo. I haven't said who are the gn yet. Right, so if I choose a sequence of predictable process gn so that this satisfies, u satisfies these conditions, so in particular the derivative will be the Malevin derivative, and this will be the second Malevin derivative. Okay. And the second that make that everything works are to choose gn of s dot to be gamma t minus s, s minus s, and as I'm choosing a sequence, this needs only to be, so it needs to be true on the infinite, so I need to work on an indicator form of a small infinite. And then a normalizing constant that is just the norm of gamma square of h in the interval 0 plus minus s. Here I should put a z. So t and x are fixed. That's the point where I'm looking at my density. Okay. Right. So that's the idea. So something similar was used in a paper by Pardue and Bali and Pardue. But for the heat equation in one-dimensional space. So what I've done here is I've used the theory of the pattern subjects to generalize this in infinite dimension. Okay, so right, so this solves the first question, and now I'm interested in another question concerning this type of equations. So maybe I will erase somewhere. Where is the array? Ah, here. Okay. Okay, so once the strict positivity problem solved, I'm interested in the following question. So if I take, so this process takes values in R. So if I take a set in R or an interval in R, and I ask which is the probability that there exists a T on X, such that UTX visit A, well, this is going to be 1, okay? Going to visit any, because at dimension 1 it visits any point, okay? So this makes this problem is interesting if UTX is something that takes values in more dimensions, but now D is the dimension of space, so let's put here, K, okay? So in order to construct a solution of a SPDE that takes values in R K, one can consider a system of equations. Okay, so now I just consider a system of equations now. So now sigma is going to be a matrix. So sum equals 1 to k, sigma ij. And this is going to be a k-dimensional family of Gaussian random variables of A, for A equals 1 of k. Okay, so if I consider a system of equations, now I have an object taking values in Rk, and I'm interested in solving the following question, which is, when is this probability strictly positive in terms of some quantity that depends on the geometry of the set, which is the capacity of the set of power alpha, which is defined to be the infimum of all the measure with support in A of the double integral of 1 divided by x minus 1 power alpha mu dx mu dy minus 1. Okay, so mu is a measure, probability measure with support in A, and this is the Newtonian kernel, right? So when alpha is d minus 2, this is the kernel associated to Bernoulli motion. So now the question is there an alpha that gives you solve this kind of problem when you use the solution of this type of SPD? Okay, so we have solved this problem for the moment in one dimension. Okay, in that one dimension we have a couple of papers with Robert Dalan and Davar Koznevichon. When we solve this problem for the heat equation in dimension 1, right? And the alpha that gives you this solution, the solution of this problem is k minus 6. Okay. Well, it was already proved by Muller and Tribe that when you have the linear equation, the critical dimension for heating point is 6. Okay, so we solve this problem for nonlinear heat equations. Okay, and for the wave equation in dimension 1, it turns to be k minus 4. Okay, and the 6 and the 4 are related to the Holder continuity properties of these equations, right? wave equation is going to be hold a continuous of the parameter 1/2 and 1/2 in time or 1/2 in space. But the heat equation is 1/2 in time and 1/4 in space, right? So it's the 4 plus 2 that gives you the power of the neutron corona, right?
Linearity is still Lipschitz.
Yes, always.
Found.
For these results, yeah, for these results you need regularity and boundedness, yeah. The only place where you don't need boundedness is to prove existence of the density, but now I'm going to give a word on how do we prove these kind of things, and for this you need boundedness. Because, for example, let me show you how we want to prove the lower bound, or the idea to prove the lower bound is that you compare the probability of hitting a set. So let's T be in T and X be in some interval of time, okay? So this is an interval of time of 0t, and this is, let's say, an interval, or maybe I will use another notation, I times j. So I is an interval of 0t, j is a subinterval of rz, okay? So if there is a tx fixed in a compact non-degenerate integral such that utx, this is the set A. So what we do for the lower bound is to compare this as the positivity of the following of the strict positivity of the functional, let's say f of utx dt dx on A times g, or this is a probability density we support in A. Okay, so this, the probability that utx hits a set, so this is kind of, if f is indicator function of A, this is the occupation measure, the amount of time that utx spends on A. Of course, well, this is formal, A needs to be enlarged a little bit, just to f to exist, and then one needs to take the limit, okay, but the idea is this, and then use Cauchy-Schwarz inequality. And this is the expectation of integral of this function dt dx times g squared divided by the expectation of the A times j f of utx dt dx squared. Right? By Cauchy-Schwarz.
Suppose that you have fractional Laplacian instead of Laplacian. I wonder whether substance this style is known for risk potential. You put alpha over 2.
Yeah, I see what you mean.
You put a risk node.
Yes, for the linear equation. For the linear, there might be.
What is known about this? Linear, non-linear.
If you put a fractional Laplacian, so I think for the linear case, okay, we so with Mohamed Fondoun and Davakos negation, we have proved that in the linear case, when you put the fractional Laplacian, you have solutions in dimension bigger than 1. Yeah, we have in some cases but then I don't know if I don't know the potential theory of this object. It might be relation.
It's natural to write a similar formula with risk potential, say
Yeah. I mean, I will say that the Rich potentials in this case are related to the existence of solutions, but not to the heating time. I don't know. But for the existence of solutions is something related to the heat. But for the heating times, I don't know. For these objects, I don't know. Right, so now if UTX has a density, and the density is continuous and strictly positive, this is lower bounded.
Excuse me.
Yes.
Looking at this formula, is it not? It seems to me that you have written the same in the
No, that's the no, the square is inside.
And here it's outside.
Uh-huh.
Okay, thank you.
Yeah, yeah. So here
You just write. I am used to another conversion. Okay.
Okay. This is what is called the second moment argument,
Okay.
the usual argument. So, right, so if UTX has a density and the density is strictly positive, this is lower bounded by some constant, U1. And now, this is so this can be written in terms of the bivariate density of the process UTX USY, right? So if the bivariate density of this process, which takes value now in RK times RK, right? So PT XSY, let's say like that. If this is upper bounded by the Gaussian density, with variance T minus S, let's say alpha 1, let me do it in general, X minus Y alpha 2, okay? Then when you take the double integral of this, then the Newtonian kernels appear. So here you get the energy, so you get the double integral, well, as a constant, double integral 1 divided X minus Y, and the power alpha is K minus 2 divided by alpha 1 plus 2 divided by alpha 2D. Of course, this you get this fx dx, big F dx, big F y di. Then okay, you get these only for probability measures that are absolutely continuous for the back measures and one. So this is the idea, but of course there's some work to do between. Okay, but the idea is that if the Gaussian if the density of the vector UTX UCI behaves as a Gaussian density, and with this form, with alpha 1, alpha 2, then here you obtain the capacity chi minus 2 divided alpha 2, 2 divided alpha 2 d. So for example, if I take the heat equation in dimension 1, this is 1/2 and 1/4, right? So here you get k, which is the dimension. So alpha 1 is 2, and alpha 2 is 4. No, alpha 1 is 1. Alpha 1 is 1, and alpha 2 is alpha 1 is 1/2, sorry, and alpha 2 is 1. So you get the 4 plus 2, which is the 6, right? Okay, so actually, so the powers are the inverse of the Holder continuity exponent. Okay, right. So that's so there are different things to do, right? So so the first thing to do is to generalize these things about the strict positivity in for a system of equations. So which is a little bit more complicated because now you have we have a matrix instead of a function, right? And what I was able to prove, so that now the result is much more technical when you deal with systems of SPDEs, and so the I was able to let me just be. So I tried to prove the same result on existence and the strict positivity of the density. So what I was able to prove is that now I have to add many conditions, but essentially the main condition is that g of t, which is g of tau, which needs to be lower bounded, remember? In this k-dimensional case needs to be also upper bounded. This is not so bad conditions. But then I was able to prove strict positivity under Holder continuity result, which is quite strong. But continuity of U plus another technical hypothesis. Okay, so under these additional assumptions, the Holder continuity of U and another technical assumptions, one can prove that UTX has a strict positive density component, on the connected component of sigma, and now sigma is the y's in our case. The determinant of sigma y is non-zero. That contains zero. Okay, so I have a very general result with some technical assumptions, and the application, I was able to show that in the case where wave or heat equation with the risk kernel, the assumptions are fulfilled. So the theorem holds. Okay, but for more general kernels, I'm not able to prove the strict positivity of the density, but actually, for example, for the wave equation in dimension 3, already Hölder continuity results are open. Okay, there's a very long paper by Dalang and Marta Sanzulé where they prove Hölder continuity of the wave equation in dimension 3 for the Ritz kernel. But when you replace for a more general kernel, it's still open. So still the Hölder continuity results are open. Okay, so it's. But anyway, because in order to apply this kind of result, so here U is, in order to apply this kind of results for U, the solution of this kind of SPDEs, the way that you're going to find a neutrino kernel here is taking the covariance to be the Ritz kernel. Okay. So actually, so let's say that the conjecture is that one can have this type of results with an alpha that can be, in the case of the Ritz kernel for wave or sheet equation, with alpha equals to k minus, and here we have something of the type 2 divided by 2 minus beta plus 2 divided by, so for beta equal to 1, I have 1. For, I think it's something like that, minus beta d. The conjecture is that we're going to have a neutrino kernel for this case. So, so the first step was to prove the strict positivity of the density, which is done. In a work in progress, so we are now trying to prove this upper bound for the Gaussian density for the case of the heat equation with Ritz kernel. Okay, so this is a work in progress. We are almost there. So, and well, I haven't talked about upper bounds, but that's an old world. But anyway, this is the idea. And another problem, which is not related to this, but it's another problem I'm looking at, is, where did I put? Ah, here. And the last problem I wanted just to talk to you about is that now forget about potential theory and return to the case of one equation. And there's so another question which is interesting is to have bounds for PTX, which lower and upper bounds. So now I have proved strict positivity, but it would be interesting to see which is the behavior of this density. And in a recent paper, again by the Eulalia Nualart and Luis Kerr, they have proved that in the case where sigma is 1, so in this additive case, they have obtained upper and lower bounds of Gaussian type, which are optimal for a small t. And what I mean by optimal is that they get the same variance, exactly the same type of bound in the lower and the upper. And the variance is actually the GT. So the integral of the Fourier transform of gamma. Right? So they prove an upper and a lower Gaussian type of the bound of the density when for a variance which is exactly equal to GT. And so they use the formula by the Enns and Norden that was presented by Frederick in the first week in the first conference. So they use this formula, this recent formula from Maria calculus that gives us an explicit formula under density that allows one to prove this type of bounds, but only in cases where there's no sigma. If you put a sigma, this formula doesn't seem to work. And with Luis-Kerr, we are now looking at a case where there's a sigma, and we are trying to use the classical method by Kusuoka-Struck, because this seems to be the only method I know that will work for this kind of SPDEs with a sigma to get lower bounds, which was then generally used a lot by Kohatsuiga. So this method is the one that seems to really work for nonlinear SPDEs to get lower bounds. And then we're going to see if the upper one also holds, and if we, I mean, for when there is no B, I'm pretty sure it's going to work. The problem is that when we put a B, there's no Girsanov theorem for this kind of equation. So I don't think if for B will work, but at least for the nonlinear case, I'm sure this will work. And that's all I wanted to say. Thank you.
Oh, sorry, am I still? Yes. Are there any questions?
You're saying that when sigma, so in the things you're trying to do now, sigma is strictly positive, has a strict lower bound, for instance?
Mm-hmm.
And you're saying you can't do any kind of Girsanov then?
No, I mean, I think it has been true that there is no Girsanov theorem because we are in dimension bigger than 1. So for this case, I've never seen a Girsanov theorem for this. And Marta Sanz told me that there is really no Girsanov theorem for this.
I mean, you have the same look that I feel. You seem surprised.
In what sense, none? I mean, just because the conditions are too strict for it to work?
It's a general Gaussian field, right? I mean, there's a
Yeah.
Cameron-Martin theorem.
I
Question about that, right?
I don't know why, actually. I don't know why, but yeah, it's a Gaussian noise, so one should.
There is no question that there's some Cameron-Martin theorem, right?
Yes, but what was the reason? I don't know. I think it's.
So what you're saying is that it's somehow too. Oh, I see. So you're.
I mean, it's for the structure of the. I don't know. I think you should ask this question as Marta because she knows better than me. But I don't know why. But why? I mean, I don't remember why. But I'm pretty sure it's true. I mean, there's no Girsanov transformation for this.
Right here.
There are some works, for example, by Andreat on the equation where the B is very singular, kind of a polynomial, and other new works on the density in for such equations.
What kind of?
No,
What kind of singularity?
The drift, for example,
It's
wave
like
equation.
1 over x or something?
No, like something like a u to power t or something like
Why
that.
is that singular?
In infinitive. In the sense it's singular that not Lipschitz, put it this way. Okay. No Lipschitz, no local, maybe some local Lipschitz.
So existence for the density of that?
Yeah. You say you can maybe, okay.
I don't know yet, but I know that Luis is working in this type of problems with Martinelli. I think they are looking at some kind of, but for the moment they are looking for existence. I mean, do you know there's existence and uniqueness in the case of non-Lipschitz coefficient?
Yeah,
Right, because the density will be after, right? But first you need to ask about existence.
Yeah, so the Martin Andreat has a lot of work on this. So
I don't know.
they maybe not know.
I don't know this work. I know that
But
they are
so
looking.
there's no work about this. So.
I know that they are looking at this and that they have they have a forthcoming paper on this, but I don't know if the kind of singularities are the same as this.
Okay.
But it's a problem that people, I think, are starting to look at for wave equation and non-Lipschitz coefficients too. But they are first going studying existence and uniqueness. Density will come after.
Presumably you don't need your number of J's to be the same as your number of I's there. As long as
No. No. For the noise, you mean the number of equations, the number of noise? I think the unit, I want to be bigger to the other to have density, but one can be bigger. No, wait. Do we need to be sigma to be a square matrix? I think that we use this in some point. I mean, I remember that for one-dimensional, you don't need to. But not here, where everything is so much complicated, I think you need to, in some point we use that sigma is a square matrix. That's what you're asking, no? If
Yes,
sigma is
that's
a square matrix. I think that in this multidimensional thing we use it at some point. To show, for using, for the strip positivity I was using it. Because the ellipticity then comes because of the ellipticity property, I think. But in general, just for the existence of the density, you don't need it. But preferably this more results in potential theory, I think that in some moment we shall be using it.
Any more comments or questions? No. So thank you very much.
Thank you.